Hello engineers, you are welcome to Crest Control Automation. This is our second live meeting. In this video, we are going to look at this diagram. It is the diagram for the traffic lights that I recently uploaded. Traffic light plays an important and crucial role in traffic or road safety management. So I'm going to explain this diagram, how it operates, okay, so that you can also wire the same thing in case you get a project somewhere. And then after the explanation, we are going to also design some basic motor starters. So let's get started. Now, this is the diagram, okay, for the traffic light. This is the stop button. Let me show it to you here. Hope you can see it. You have the stop button here, okay? Yes. So this is the stop button. This is the stop button. The start, the selector switch, okay? Yeah. And then this is the traffic light itself. You can see that it is working, okay? This is the green. After some time, you see that the red is on. Yes. See that? So when the green goes off, the yellow will come on for some time, and then the red will be on. Okay, so this is how it works. Okay, so let's explain the diagram. So with the diagram, all right, we have this component. This is the stop button. This is the start button. Before I continue, let me address those who are here. We have Daniel Teye Huago. Yes, I am waiting patiently. That's good. We have Set Industrial Control Automations, very ready as usual. Here in Uganda, you are all welcome, engineers. Let's continue. We have the stop button, the start button, and then this is our relay 1, okay? This is a hold on for this relay. This is the selector switch. You see this switch? Yes, this switch is this, okay? The selector switch. Yes, this is the R7, relay 7. This is the timer. This is R7, okay? Close contact on this R7. This is an open contact on this R1. That is the main control relay. So the moment this relay opens, all the circuit will be off. All right. Now, this is a close contact on this timer. Yes, this is a close contact on this relay. This is an open contact, okay, on the R8. This is R8. Yes, this is relay 2. Relay 2, this is timer 2, close contact. Timer 1, open contact. Relay 3, okay. Yes, these are all open contact on the R8, R7. We have R3 open, R4 open, T2. So now let me begin with explanation. Okay, as you can see, as I showed you, you see that the red light is on, okay? After some time, it will go off, the green light will come on. You see that? After some time, it will go off, the yellow light will come on to serve as a ready light, ready. Yes. So after some time, it will also go off and then in that order. You see that? You see that? So now, when we press on the start button, this R1 will energize. So when this R1 energizes, this contact will close. This is a main hold on for this R1. Okay. So when this R1 closes, let's see. This is our live line. Live 1. This is the neutral. Okay, yes. So when this R1 energizes, okay, this is a hold on for this R1 so that when we take off our hand from the push button, still current will flow through here to maintain this R1 in energized state. Now, this R1, an open contact on this, it will also close, okay, so that it will provide current or power for the whole circuit. Okay, so as this R1 is closed, current is flowing through to this point. The moment it gets here, because the selector switch is in open state, it can continue to energize the R7. You see that? Okay. Now, Current will flow through, because this R6 is a closed contact. Current will flow through this closed contact on the R7. Okay, then it will energize the timer, the T1. So this timer is energized. The same current will also flow through here, through this closed contact on the timer. Okay, now you see here, I've written here red. We have the red. This is the red circuit, the red relay. This is the green relay. Okay, this is the yellow relay. So R2 is for red, R3 is for green, and then R5 is for yellow. Okay, so now as current is flowing through this closed contact on the timer, through this closed contact on the R7, okay, it will energize R2. So when the R2 is energized, the red light will be on. This red light will be on. So now our timer is also energized. So it is counting, okay? Now after the preset time, when this timer finish counting, okay, this is a close contact on this line. So this close contact on the timer, it will open. The moment it opens, this R2 will de-energize, and then the red light will go off. Okay, so as this contact is open, this is also a close contact, an open contact on the timer. So it will close. When it closes, now we have another T2 contact, which is also closed. So current will flow through this close contact on the timer 2, and then through this close contact, okay, on timer 1, because the timer has finished counting. That is why this contact is closed. So current will flow through to energize the R3. So it means that the green light is also going to come on. The green light will come on. The moment the red light goes off, this green light will come on. Okay, so now as the R3 is also energized, okay, and then the green light is on, we have another R3 open contact at this point. So the moment the R3 energizes, this contact will also close. So when it closes, we have close, and then current will flow through here to energize the T2. Okay, so when the T2 energizes, because I have parallel the R4 and T2 together, so it means that the R4 will also energize at the same time. So T2 and R4, they will energize at the same time. So now, as the R3 is energized and then the green light is on, okay, the T2 is also energized. So it is counting. The T2 is counting. Okay, it is counting. So after its preset time, we have a close contact here on this T2. So when this T2 finish counting, this contact will open and then the green light will go off. Okay, to go off. Now let's look at something here. We also have another open contact on this T2. So when the T2 finish counting and then this contact opens, this side is going to close and then the yellow light will come on. You see that? The R5 will energize. You see that? When it closes, current will flow through to energize the R5. So when the R5 energizes, you see that the yellow light will be on. And then the R5, I paralleled the R5 with T3. So they will all energize at the same time. So now our R3 is de-energized. Okay, and then our R5 is now energized and yellow light is on. So the T3 is also energized and then it is counting. Okay, the T3 is counting. So after its preset time, we have T3 open contact here. So when this preset time reaches, this contact will close. So when it closes, the R6 would energize. So when the R6 energizes, I brought a close contact here. Okay, this is a close contact on R6. So the moment the T3 finish counting, okay, and this contact closes and the R6 energizes, this contact is going to open. So when it opens, the whole circuit is going to go off. So let's see something here. Let's see something carefully here. When this R6 opens, okay, the whole circuit will go off. So including that R6 itself, it is also going to de-energize. The moment it de-energizes, okay, because this contact is open, you know, because this contact is open, the moment it de-energizes, this contact will become closed again. It will become closed again. So when it closes again, automatically this T1 will energize because current will flow through here, through this closed contact to re-energize the T1. At the same time, current will also flow through this T1 closed contact, through this closed contact on the R7. And then the R2 will also energize again. So it means that we have started all over. Okay, we have started all over. So I'm going to switch. I'm going to operate it and then we see how it is. Okay, yes, so let's go there. Okay, so we have the selector switch, the stop button and then the start button. Okay, so this is our traffic light. Okay, it is already working. So I'm going to press on the stop button. So I've pressed on it. Okay, now it is off. So I'm going to press on the start button. The moment I press on the start button, the red light will be on. So let's see. You see that the red light is on. So after the preset time, the green light will come on. Okay, yes, the green light will come on. So let's see. You see that the green light is on. After the preset time, it will go off and then the yellow light will also come on in that order. So let's see. You see that? And then, yes. So you see that it has started again. So that is the work of the RCs. Okay, that is the work of the RCs. This RCs I showed you. This RCs. That is why it started all over. So to be doing that over and over and over again until you stop it. Okay. Yes. So this is how it operates. So this project, I sold it to someone. Okay, I sold it to someone, but because you are all my subscribers, I am giving it to you for free. Okay, so this is how it operates. I sold this diagram for someone. Yes, but because you are my subscribers, I am not going to sell to you. So just take it for free and then make sure you can even use this project as your school project at the university level or the polytechnic. Okay, yes. So now, we are going to look at another important area. Let's see here. The reason why I brought this selector switch, I am also going to explain the reason why I brought it. Okay, all right. Now, I don't know whether you have noticed traffic light operation. You see, during the daytime, okay, the traffic light, they will be changing like this. They will be changing one after the other, like this. Okay, yes, they will be changing like this, one after the other. You see that? Yes. But during the night time, you see that around somewhere around 12 o'clock a.m. in the night, between 12 o'clock a.m. to 5 o'clock a.m. Okay, that is when no cars will be moving. In that period, you see that all the three lights, they are all flashing at the same time because they have programmed them, and then they are all flashing at the same time. So we are going to look at how that one also looks like. Okay, yes. So I brought this selector switch for that particular process. Okay, let me come back. Obiba chapters, thank you, engineer, for the good work. Yeah, thank you very much. Vincent Zoya, keep it going. Engineer Chris, good. Yeah, Vincent Zoya, thank you very much. Okay, Daniel Teyehuago, you are always the best. Thank you, Mr. Daniel. Thank you. Thank you for you being loyal subscribers. Yes, you are going to learn a lot in this channel. Yes, every Saturday through life. Okay, now you see the selector switch. Okay, you see there's the selector switch. So assuming that let me come back before the lights will operate, all the three lights will operate or will flash at the same time. There is something you call RTC. TC model. RTC model. The R means real time clock. Okay, this model, RTC model, mostly traffic light, you use PLCs, okay, to design them. That is why I use this PLC. This is my PLC here. Okay, I don't know if they can see it. Yes, and this is the power supply. This is the power supply that you are seeing here. Okay, yes. So mostly they use PLC, okay, to design the traffic light system. They use PLCs. So now let's see something here. I'm coming, eh? Okay, so I am setting something here. Yeah. Okay. All right. Yeah, my stand is not standing well. All right, you can go on. Okay, so as I was saying, now this model, okay, this model I was talking about, the real time clock, it is always embedded in the PLC. So they have always programmed this real time clock. It's a clock model in the PLC. So they've done it in such a way that they've timed it so that around 12 o'clock a.m. in the night, automatically the traffic light, okay, it will switch this way. Let me turn the selector switch so that you see how it is. Okay, I am switching on the selector switch. Let's see. You see that they are all blinking at the same time. So this work, they have used this model, the RTC, to time it that around 12 o'clock a.m. automatically the traffic light, they will start blinking or flashing at the same rate. It means that during that time no cars are moving, or if cars are moving, there are just few cars. Okay, because we have entered into the off peak mode or off peak. That time there are no cars moving. So around 12 o'clock a.m. to 5 o'clock a.m. the light will be flashing this way. I don't know whether you have noticed that. If you have been to traffic lights around those period, around 12 o'clock a.m. midnight going, you will see the light flashing this way. So it means that they have used this model, the real time model, real time clock in the PLC to monitor it. Okay, so at 5 o'clock a.m., exactly 5 o'clock a.m., this light, they will go back to their normal state like this. Okay, assuming I've switched off the setup switch, so they've gone back to their normal state like this. You see that? So that is how it operates. Okay, you see now it has started the normal operation. Okay, so let's go back to the diagram. Now, this diagram, okay, I brought the selector switch, this selector switch here. So the moment I turn on this selector switch, let's see what happens. When I close this selector switch, the R7 would energize. This R7 would energize. So when it energizes, let's see here. I use a close contact on the R7 in series with the timer line. So the moment this R7 energizes, this contact will open. At the same time, I also use the same R7 in series with the R2 line. So this contact will also open. Okay. Now let's come here. I use the same R7 here on this timer T2 line. So this contact will also open. At the same time, I use an open contact, this contact on the R7. So this contact will close to provide current for this circuit. Okay, so let's see what will happen. Now, the moment this contact closes, okay, this contact is called flip-flop. This is a flip-flop, flip-flop, flip-flop. Okay, you can use IC to do that. Okay, but I'm using timers and relays to do that. So now, the moment this contact closes, okay, current will flow through this close contact. This is T5, timer T5. Okay, it is a close contact on this timer. This is the timer. So as current flows through this close contact, it will energize timer T4. At the same time, current will also flow through this close contact on timer T4 to energize R8. So let's see something here. The moment the R8 energizes, okay, I brought an open contact here in parallel with this line. And then this line, okay, this line is the R2 line. The R2 is the red light. Hope you have seen it. The R2 is the red light. So as the R8 energizes, this contact will close, and then it will provide a bypass current, okay, to energize the R2. I also use the same open contact on the R8 also here. So to also provide a bypass current through this close contact of the R8, and then it will energize the R3, which is the green light. You see that? I also use the same R8 contact here. So it will close, and then to provide a bypass current, okay, to energize the R5, which is the yellow light. So it means that the moment the R7 energizes, and then this contact closes, okay, this R2, that is the red light, R3, the green light, and then R5, the yellow light, they are all going to energize at the same time. So now, let's come back to the flip-flop. So you see that the T4 is energized and then it started counting, right? So after the preset time, this contact is going to open and then the R8 will de-energize. So it means that when the R8 de-energizes, okay, the R2, that is the red, R3, the green, R5, the yellow, they are all going to go off. You see that? So as this contact is open, it's a closed contact on the T4. So as it is open, this contact, the T4, is also an open contact on the same T4. It will also close and then to energize, that is T5. So when T5 energizes, okay, during that time, the R8 is de-energized because this contact is open. So this side is closed to energize the T5. So as the T5 is energized, it is also counting. It will count. It will count. After its preset time, I gave them 1 second. Okay. The moment it is finished counting, this contact will open. The moment it opens, okay, the moment it opens, the T4 is going to de-energize. So when the T4 de-energizes, this contact is going to go back to its closed state. So when it closes back again, current will flow through to re-energize the R8. And then the green light, the red, green, yellow, they will come back again. So it will be flashing. So this is a flip-flop. This circuit is a flip-flop, okay? You can use 555 timer to do it. 555 timer. IC. You can use this IC to also do the same thing, but I use relays and timers to also replicate the same thing, okay? So that is why when you turn on this selector switch, okay, the light will be flashing this way, on and off. So now, I use selector switch in case I want to let the flashing happens automatically. If I want it to flash automatically, what I'll do is, okay, I'll get external timer. If you don't have a PLC, you can get external timer, and then you program the timer that from 12 o'clock a.m. okay, from 12 o'clock a.m. close the selector switch. Okay, the moment the selector switch closes, and then the timer, the traffic lights, they will all flash at the same time. So in place of the RTC model, okay, you can use the selector switch. In case you want it to operate automatically, then you can use an RTC model or backup. You have to get a battery. The reason why I'm saying that you have to use a battery is that sometimes there can be a light out. So if you don't have a backup battery that is there, okay, you lose everything. So the moment the light goes off, because there's a backup battery, it will take over, and you wouldn't see even if there is a light out. So that is the basic operation of this traffic light. So I'm going to operate it once again, and then we all see how it is, okay? So now that is it. Assuming it is 12 o'clock a.m. So like this, you see that? You see it is flashing, okay? Yes. So I use this relays. Let's see this relays. Have you seen this relays? The 3 relays, you see that? So the signals are coming from the PLC to energize these relays. You see that? 1, 2, 3. This is red, yellow, and then green. Okay. So I am waiting for questions. So now, assuming that it is 5 o'clock a.m., okay? So I'll turn off the selector switch. So let's see what will happen. See that the red light is on, and then it will operate one after the other. So this is an intelligent traffic light system, okay? You see that? So it will operate like it used to be. As I said, this is a big project. You can build it in your schools, okay? Yeah, so I want to answer some questions, and then we move on to motor status. I want to answer some questions, and then we move on to motor status. Yeah, let me read some comments here. We appreciate you, Mr. Augustine. Yeah, thank you very much, Mr. Augustine. Samuel Saki, keep going. Yeah, thank you very much. I welcome you all here to today's live. This is live 2. Live 2. So I want to see some questions on the traffic light before we move on to the motor status. Yeah, I am waiting to see some comments or some questions regarding this diagram. Yes. So if there are no questions, then I'll move on to the motor status. If you are all here, I want to see that we are here. Kindly give me some hi. Okay. Set industrial control automations. Here in Uganda, red light is for stop. In case there is a traffic jam, how can I connect traffic light so that the red light to hold on for specific time when there is a long lasting traffic jam? Okay, that is a very nice question from Set Industrial Uganda. Yeah, you see that in case you want the red light, okay, to stay on for a very long time, what you do is you just increase the time setting. Assuming this is just for demonstration sake, okay? Yes, I am only demonstrating it. But in case I want to install it in town for the main project, I will increase the timer T1, this one. I will increase it to, let's say, 1 minute or 2 minutes, so that this red light will stay on for 1 minute, okay? You can equally do the same thing for the rest. If you want the green light to also stay on for 2 minutes, you just increase the timer T2 settings, okay, to, let's say, 2 minutes. So, Mr. Set, if I have you are okay with the answer, let me know so that I continue. Adoko Dominic, hi, Mr. Adoko, you are welcome to today's episode. This is live 2. Live 2. Yes. So if there are no more questions, Mr. Set, are you okay with the answer? Is your question answered so that we continue? Okay, answered. Thanks. All right. Thank you very much for your question. Now we are moving on to motor status. Yes, we are not going to keep a bit longer. Motor status. Now we have various types of motor status that we use in the industry. Okay, so let me list some common ones that we have. Okay, so we have I'll start with direct online starter. Direct online starter. 2, I'll start with forward, and then reverse starter. I'll continue with star data, starter. And then we have 4, auto transformer. Starter. 5, we have starting reactor. Starting reactor starter. 6, we have variable frequency drive, VFD, or variable speed drive, or inverter. Okay, 7, we have soft starter. We have soft starter. 8, we have what again? We have liquid resistance starter. Liquid resistance starter. You can call it LRS. Okay. Yes. So there are many, but these are the common ones that you use in our industries. Okay. Yes. This one you can equally call it roto resistance starter. Roto resistance starter. Okay, the LRS, because they operate hand in hand. All right. Yes. So these are the basic types of starters that we have in the industries. Okay. One question, Patrick Belfi, engineer. In case there is light out, can you add ATS connection to this connection, both ECG and battery? Of course, yes. But the reason is, okay, you have to get a battery backup so that you see the moment some of the RTC model, okay, these models, some of the RTC models, the moment they lose power, okay, and when the power comes back, they start all over again. Assuming it has time up to, let's say, we have set, let's say, 12 hours, and then during the time there was light, it has timed up to, let's say, up to 6 hours. Okay, let me explain your question for you. So the moment there is light out and then there is no battery, and this RTC model, okay, the moment it loses its power, all this 6 hours reading it has read, okay, it will go off. So when the light comes back again, it is now going to start all over again. So assuming the light went off around 5 o'clock p.m. 5 o'clock p.m. and then the light comes around somewhere 7 p.m. or 5:30 p.m. Okay, the moment the light comes back, this RTC model, the memory will reset. Its memory is going to reset, and then when the light comes back, it is going to start from zero again. So it means that, let's say, if you have timed it that it should change or it should switch to the flashing at 12 o'clock a.m. because it has started or it has reset. It is done when it get to our normal time. When our normal time get to 12 o'clock a.m., there's no way it will switch. It will change because it has started over. So the most important thing is that always this RTC model, it shouldn't lose its power. So make sure you connect battery. And then most of the PLCs, they have inbuilt battery. This PLC that I'm using, okay, it has the RTC, but it doesn't have inbuilt battery. So in case there is light out and then the light comes back, this RTC, it is going to start all over. Okay, so when you connect ATS, that is automatic transfer switch, ATS, okay, then make sure that the moment the light goes off, the ATS will start, and then the power will still be applied to this model. And mind you that when the genset starts, okay, when the power goes off, the power will go off before the genset will start. And when the genset starts, it is not at the same time we are going to get the genset power. It will start and then it will take some speed before we get the power. So make sure you have battery, okay, connected to this RTC model. So assuming that we have the model like this, okay, this is the model RTC, and then this power is from the PLC, okay, the PLC connected to the RTC. Make sure you also have another battery backup like this battery, all also connected to the RTC model. So assuming this PLC goes off, okay, still power is still there, and this RTC will never go off, and in that case it is not going to lose its memory. Engineer Belfi, Patrick, am I okay? Have I answered your question? If I've answered your question, kindly let me know so that we continue with the motor status. I'm waiting for you before we continue. Engineer Patrick Belfi. Okay, so now I will continue whilst we wait for your answer, your final feedback. Yes, engineer, thanks. Okay, okay, all right. So now these are basic starters that we have. Okay, we have direct online starter, forward and reverse starter, star delta, auto transformer starter, starting reactor. Auto transformer and starting reactor, they are almost the same. This one, okay. Auto transformer and starting reactor, they are all almost the same. Okay, yes, they are all part of parts winding starter. They are part of parts winding starters. When you talk of part winding starter, because it's a winding, okay, that has tappings on it that you can use it as starters. And then this auto transformer and then the starting reactor, they are having these windings, so they are part of this. We have part winding starters, so they fall under this. Okay, now we have the VFD or VSD or inverter, variable frequency drive, variable speed drive or inverter. We have the soft starter. Okay, the soft starter and then the VFD, they are slightly the same, slightly. Yes, and then we have the liquid resistance starter, LRS, or roto resistance starter. Okay, these guys too, they are also having the same operation. Yes, this one. Okay, so today we are going to look at direct online starter. Okay, we are going to look at direct online starter. But before then, I want to explain all these starters before we continue with the direct online. Now, direct online starter is used for small motors where the starting current, okay, the starting current is fully applied to the motor. So assuming you have a motor from 0 kilowatt to, let's say, 7 kilowatt, you can start this motor on direct online. So it means that when you energize the contactor, okay, full voltage and then full current is going to be applied to the motor. And because the motor is not all that big, it is 7 kilowatts, okay, it will never have any effect on the supply lines. Okay, so usually you use 7 kilowatts, you can use even 8 kilowatts, 8 or 11 or 10 kilowatts. You can use them all on direct online starter. Okay, so that is the working principle of direct online starter. The reason why you use direct online starter. Now we have forward and reverse. Forward and reverse is also direct online starter. Forward and reverse, it is also direct online starter. But the main difference is that this one, it operates forward and reverse. It is two direct online starters. Okay, like this way. This is one, and then this is another one. You tap from here to this side. So this is the forward line. This is the reverse line. Okay, yes. We have star delta. Star delta. Star delta is used on motors above 10 kilowatts. Okay, going, let's say, from 10 kilowatts to, let's say, 20 kilowatts, 25, 30. You can use star delta for them. Okay, star delta for them. But why do we use star delta? That is the main question. We use star delta whereby we want the starting current and then the starting voltage to be reduced. Okay, so let's see here. We have, let's say, 415, 415. This 415 is supposed to be applied to the three-phase motor. Okay, this is our three-phase motor. All right, now when you use the star delta, it means that we are going to use half or 1/3. Okay, this voltage multiplied by, sorry, you can do it 415 over root 3. If someone have some calculator, you can do the calculation and then you give us the value. When you do this, okay, you are going to get 240. Okay, 240 volt AC. 240 volt AC. So it means that when you apply, okay, the voltage in star configuration to the motor, okay, it means that we have divided this 415 voltage, or we have reduced it to 240 volt to the motor. That is the main reason why you use star delta. Star deltas are used for motors that draw high current on starting, motors that draw enough current or high voltage on starting. So when you use star delta during the star configuration, okay, we are going to use 240 volts, okay, in the motor. But when the timer, okay, the timer preset time reaches, the star will go off and then the delta will take over. So when the delta takes over, then it is going to apply 415 volts, okay, 415 volts to the motor. And during that time, the motor is already going because it started in star, that is 240. So when the 240 go off, the motor will still continue to operate. So after the preset time, the delta will take over and then 415 will apply to the motor and then it will increase the speed again. So in that case, less current is going to what? Is going to be withdrawn, less current, and then there's not going to be any voltage drop on our supply lines. So that is the main reason why you use star delta. Now we have auto transformer starter. Auto transformer starter and starting reactor, they are also the same thing, okay? They operate the same way. So let's see here, like this. We have winding like this, okay? And then we have tappings. The tappings, mostly we have 80%. 80%, we have 65%, and then you have 50%. So this is auto transformer starter. It is a one winding which has tappings on it. So assuming we apply a three-phase voltage, okay, this is our line 1. This is our line 1. We apply the voltage to this first winding, okay. And now these are coils. They are like this, coils. So assuming we tap from 80%, it means that you have used 80% of the supply voltage, let's say 415 volts, okay, 80% of this, okay. On the, you have used 80% on the motor. So it means that you are going to apply this line, okay, to the three-phase motor. In case we want to use 65%, it means that we use this winding plus this section. So we have increased the winding resistance small. So it means that there's going to be a large resistance over here. So when you use 65%, it means that you have also used 65% of the 415 volt. So if someone has a calculator, the person can punch it and then you get the values here. When you want to use 50%, okay, it means that you have used this winding, and then this winding. So it means that the voltage is going to be something. Assuming 50% is half. So 415 over 2 will give us like let's assume 207, okay, 207.5 volts. So when you use 50%, it means that you are going to apply 207.5 volts to the motor windings when you use 50%. When you use 65%, just do the calculation, okay? So that is the reason why you use auto transformer and then starting reactor. Auto transformer and starting reactor, they are all reduced voltage starters. We use them to also reduce the starting current and then the starting voltage when we start the motor at first. Okay, the moment you press on the start button, okay, and assuming you use 65%, it means that you are going to apply 65% of the three-phase voltage to the motor. That is the main reason why you use auto transformer or starting reactor, okay? They are all the same. Now, we have VFD, variable frequency drive. VFD is also a reduced voltage starter, but VFD is used for regulating the voltage applied to the motor at any time. These ones, auto transformer starter, starting reactor, they are fixed. If you want to change the voltage, okay, or if you want to reduce the speed or increase the speed, then you have to come back to the windings and then you change the tappings. Assuming at first it was on 80%, and then you want the motor you want the motor speed to go down a bit, then you can change it to 65. But with the variable frequency drive, you just rotate the knob and then the speed is increasing or decreasing. It is so simple. Soft starter is also, let me say, the same as it operates similar to star delta or VFD because it is also a reduced voltage starter. Let me say it is almost the same as star delta because when you start the motor, okay, a section or a percentage of the voltage, okay, is going to be applied to the motor. So in that case, the motor will operate slowly on low speed. After some time, okay, then it switches onto or it switches on the high current contactor. There are contactors in them. So to switch to energize the contactors, and then they will apply the full voltage to the motor. But during the starting, it uses this one thermistors. It uses thermistors or SCR or IGBT. These are all transistors, high power transistors. Okay, yes, thermistors, silicon controlled rectifier or insulated gate bipolar transistors. Okay, they use this component, this electronic component, to do the starting at initial start. All right, let's go to liquid resistance starter, LRS, or rotor resistance starter. They are all reduced voltage starters. This one, okay, we add some resistance, okay, in the rotor circuit. Assuming this is the rotor, this is the rotor. This is the rotor, okay. Yes, this is the rotor. So they have two ends. I'll add some resistance, okay, in the line, so that when I apply the power to it, the current will be reduced. Okay. Yes. So these are the basic starters we normally found in industries. So we are going to draw direct online starter. I'm going to draw direct online starter. Okay. All right. Direct online. We have the power side. You see it. We have the power side, and then we have the control side. So this is the controls. Okay. So the power. We have our three-phase line like this. We have line 1, line 2, and then line 3. Okay. Now we have, let's assume we have our breaker here. I'll draw it a block, okay? Yes. We have our contactor like this. Okay, so now I'll tap from line 1 to this side. I'll tap from here, and I'll tap from here. This side will go to the contactor. Okay, and then from here it goes to our overload. Okay, now this is our three-phase motor. So three-phase motor. All right. Okay, so the contactor we have 1, 2, 3, 4, 5, and then 6. So this is our contactor, K1. Okay. All right, and then this is the overload. This is the overload. All right. So this is the power. Let me say this is MCCB, molded case circuit breaker. Yes. So this is our power line. I want to show you a picture of MCCB. Yes, this one is MCCB, okay? You see, yeah. So we have the 3 input and then the 3 output. This is MCCB. All right. So this side. So this is the power side. Now, our main aim is to apply, okay, 3-phase power to this motor by energizing the K1. So why do we energize the K1? Should we go and press on the K1? This is the K1, this contactor, okay? Should we go and press on this button here, on this knob here, this thing, this plunger, this is a plunger. Should we press on this to apply power to this? Then it means that we are going to get tired. It is nonsense. So in that case, we have to get a control so that we can even sit in our hall, in our bedroom, in our factory, in our control room to operate the motor at a far distance. Okay? To operate the motor at a far distance. Now, let me answer some few questions here. Mr. Patrick, please, engineer, when you finish, please list motor kilowatt that we can use DOL star delta starter. I mean all the starters and its kilowatt motor to be used. Okay, I hear. I'll list them. Ty Wood, please, engineer, can I use DOL while the motor is connected in delta in the terminal box? Okay, this question is also good. Yeah, I'll answer it. I'll answer you, okay? But let's finish with the diagram first, okay? Yeah. You see this. This is the power contactor. That's the K1. So assuming I want to operate the motor, I don't have to go and press on this knob. It is not practically correct. Okay, it is not correct. So, but I want to control this motor or energize this contactor from a far distance using a control circuit. So now, this contactor, it has coils. We have the A1, we have the A2. This is where we energize the contactor so that when it energizes this plunger, it will pull inside, okay? It will be pulled inside. So how do we control or energize this A1? That is with the use of control circuit. So control circuit, because our contactor is a single phase contactor, I only need live and neutral. Assuming the contactor is a 3-phase contactor, therefore I will use 2 lives, okay? But because this contactor is a single phase contactor, we are only going to use live and neutral. So our control circuit should have live and then neutral, okay? So this is our line 1. It can be line 2 or line 3, just only one live. Okay, now see something here. We have our overload. This is overload, okay? Overload relay, thermal overload relay. Why did I use the overload here? I use the overload because when there is a fault, okay, the current flowing through the motor will increase. So the overload heaters, these are called heater. It is called heater. So these are heaters, 1, 2, 3. They are all connected in series with the line. So assuming 10 current, 10 amps of current is flowing through the motor. Okay, yes. So during under normal circumstance, okay, these heaters, they will not get heated because 10 amps is flowing. But the moment there is a fault, okay, or there is overload, the motor would begin to draw more current. So as the motor is drawing more current, okay, this current that is set on the overload, it will increase. So assuming it increases to 11 amps or 12 amps, so when it increases to 12 amps, okay, 12 amps is going to flow through the line. The moment it flows through the line, these heaters, they are going to get heated. They are going to heat up. So when they heat up, we have this contact, this close contact, this auxiliary contact on them, and then we have some plunger. Okay, they are like bimetallic strip. It will bend. When it bends, it will push this plunges, and then this close contact, it will open, and then this open contact will close. When it cools down, and then it comes back to its normal state. Okay, so that is the working principle of the heater. So we are going to use this auxiliary contact, the close contact, this close contact. Okay, mostly it is 95 and then 96. Okay, so we are going to use it in series with the main line that will energize this coil. Okay, so assuming this overload heaters, they sense high current, this contact is going to open. So when it opens, then current will cut off from the A1. All right. Okay, so from here we tap it to 95, 96. Okay, we have 95 and 96. So this is 95, 96. From here we take it to our stop button. So this is stop, that is 1 and 2. From here we take it to our start button, that is 3 and 4. All right, then it goes to the K1, that is A1 and then A2. Because I said our contactor is a single phase contactor, we only need live and neutral. So this is the live line, this is the neutral. So we give here neutral. Okay, this is our neutral line. Now we connect a hold on contact, that is 1314. Okay, in parallel with the start button. This contact is 1314. Okay, it is on this K1. So we write here K1. Now, when you press on the start button, okay, current will flow through this close contact of the overload, through the close contact of the stop button, and then to energize the K1. K1 will energize. Therefore, the moment it energizes this plunger, it will go inside, okay, and then power will be applied. This contact will close. Then power will be applied to the three-phase motor. All right, this contact is there to close. The moment the K1 energizes, it will close to serve as a hold on, so that when we take our hand from the start button, okay, this contact will open. But because this contact is closed, current will still flow through to maintain it. Now, let me come back to this side. Assuming there is abnormal current, okay, the overload heaters, they sense high current. Okay, they will heat up and then they will burn. It's like bimetallic strip. It will burn. When it burns, it will push this plunger. Okay, this close contact. And now we have used this close contact, okay, in series here at this point. So the moment it pushes it, it's open because it has sensed abnormal current. So when it opens, this contact will open, and then current would cut off from this line, and then the A1 or the contactor will de-energize. When it de-energizes, this plunger, okay, it will come back to the top position. Means that we have opened the contact inside here. All right. So that is basically the power and then control diagram for direct online. Now I am answering some questions. Yes. Okay. Mr. Patrick. Okay. All right. I will list them. Okay. Yeah, I will list them. Maybe later after the video. Mr. Tywood, please, engineer, can I use DOL while the motor is connected in Delta in the terminal blocks? Yes, you can use it, Mr. Tywood. You can use it, okay? So assuming that, let me say, the motor terminal block, we only have two connections. Let's assume this is motor 1. So we have the terminals, there are 6, okay? 3 here, like this. This is another motor, also 3. Okay, mostly we have the U1, U2, U1, V1, and then W1. We have W2 here, we have U2 and then V2. The same thing here, okay? U1, V1, W1, W2, U2, and then V2, okay? So now, if you want to operate this motor using direct online, you can do it either star. So in star, you just bridge these 3 lines. That's all. If you want to use direct online on Delta, okay, you just bridge like this. So, Mr. Tyrone, this is your answer, the question you asked. So you can use it, okay? If it is answered, let me hear your question. Let me hear your feedback if your question is answered. So here you can apply direct online here. You can apply direct online here. Okay. I have done them. I have done them. I have done the video. So go to my YouTube channel. Okay. You see these videos. They are all there. Okay. Yeah. Mr. Set industrial control automation. Engineer, don't we need a transformer to step down 240 volt to 220 to supply to that coil of the contactor you are holding? Engineer, Mr. Set, 240 and then 220, they are all the same. They are all single phase voltage, okay? Yes, so you don't need any transformer. Yes. All right, so is that all? Then I think we are going to end the live for today. Next week, if God willing, we are going to do something great. We are going to do a lot of automation diagrams. So make sure you share the links to your friends. You tell them to join next week. Tyrwood, thanks a lot. Well answered. Okay, Mr. Tyrwood, I appreciate. I appreciate all of you who had your time to learn today. Indeed, I value you all as my subscribers. Yes, so let's keep it up. Okay, I will be answering all your questions. You are going to learn a lot of diagrams. I'm going to teach you how to design your own control diagrams. So it is step by step, okay? Yes, so next week is going to be something different. I will communicate it using the link. All right? So if there are no more questions, set industrial control automation. Thanks, Mr. Chris. Love you so much. Mr. Seth, I also appreciate you for having the time to watch today's video. Yes. This is great. I'm always grateful to have you all as my subscribers. Yes, let's grow together. Let's grow the channel. You are going to learn a lot. Okay, Mr. Patrick, still waiting for the list. Okay, Mr. Patrick, let me give you a small gist. Okay, now for direct online DOL, you can use 0 kilowatt to 10 kilowatt. Okay, for star delta, you can use from 10 kilowatt. Okay, from 10 kilowatt to, let's say, 10 kilowatt to, let's say, 30 kilowatt and even above. You can use them. Okay, let's say 10 kilowatt to 30 kilowatt. These values are not constant. The reason being that assuming that you are using 20 kilowatt, okay, in star data to push water. You see that you are using 20 kilowatt in star data to push water, and then someone is also using, let's say, 10 kilowatt to push let's say stone. Okay, 20 kilowatt is pushing water, 10 kilowatt is pushing stone. Now let's all be sincere. Stone and water, which one is heavier? Stone is heavier. So though the 20 kilowatt is bigger than 10 kilowatt, but I can use this 20 kilowatt in direct online. You see that? I can use 20 kilowatt in direct online, and I can use this 10 kilowatt in star data because it is pushing stone. And if I'm to start the motor on full speed, it is going to trip breakers, it is going to blow fuses, it is going to draw high current. So though this 10 kilowatt, I can use it on star data, but the 20 kilowatt, I can use it in direct online because it is pushing water. Water is very light. So engineer, these values are not static, okay? But the rule of thumb is that 0 to 10 kilowatt, you can use DOL and this, but it doesn't apply in all situations. Yes. Okay. Vincent Zoya, we really appreciate all great works. Thanks a lot and have a great one. Mr. Vincent, thank you very much for your time. For today's episode, next week is going to be something practical, practical. Okay. So let's all make it a date and then also meet next week. Mr. Patrick, I hope you understood the explanation here. Yes, they don't apply in all situations. Okay, every situations and how we are going to install it. But the rule of thumb, okay, says that use this for that, use this for this. Okay, yes. If there are no more questions, I would end here and then, God willing, next week we continue. I value you all. I love you all. Have a great weekend. Thank you all.